Good evening, everyone. I am Dr. Samik Mukherjee. I'm a faculty here at Geo Institute. It is a great pleasure to welcome you all to today's session of this Fusion Energy Masterclass series. Today's session is particularly special for us, and we are deeply honored to host Dr. Pietro Barabaschi, the Director General of the ITER organization. Thank you very much, Dr. Pietro, for taking the time to join us and engage with this initiative. Across our previous masterclass sessions, we have explored the fundamentals of fusion, the underlying plasma physics, India's role in global fusion programs, the concept of burning plasma, and most recently, the transformative capabilities that are pushing fusion closer to reality. Today's masterclass brings us to the center of the global fusion effort, the ITER. In many ways, ITER represents the most ambitious scientific collaboration ever undertaken by mankind, bringing together countries, institutions, scientists across the world to demonstrate the feasibility of fusion as a large-scale energy source. Also, to help us reflect on some of these scientific and strategic dimensions, we are fortunate to have with us a set of distinguished panel members. We had Dr. 𝗍𝗫𝘆 𝗧, the project director, who left briefly for another meeting. Dr. Ranjay Sharan, distinguished scientist, Department of Atomic Energy. Dr. 𝘍𝘶𝘴𝘆𝑚, Professor Emeritus, the Institute for Plasma Research, 𝘍𝘶𝘴𝘵𝘀 𝘧𝗸𝗏𝘄, former Associate Project Director of ITER India, Dr. 𝘠𝗀𝘆 former Project Director, ITER India. Also in some time will be joining us Dr. Rajesh Miyangi from Princeton. Thank you, panelists, for joining us. It is now my honor to introduce today's speaker. Dr. Pietro has served as the Director General of the ITER organizations since 2022, overseeing the reforms and the construction of the ITER project. He joined the ITER team in 1993 during the early engineering design activities of the project, working across 3 international joint work sites, that in Munich, Germany, San Diego, California, and Naka, Japan. In 2000, he was appointed deputy to the ITER project leader and head of the engineering and design integration unit, playing a key role in coordinating the complex design efforts of this global project. In 2006, he moved to Fusion for Energy, the European agency responsible for delivering Europe's contribution to ITER and also to broader approach, a collaboration between Euratom and the government of Japan, where he led the Fusion Development Department and oversaw major projects, including the 𝗤𝘗60 tokamak. He also served as the acting executive director of Fusion for Energy in 2014 to 15 and again in 2022 before taking on his current role as the Director General of ITER organization. He was a recipient of the US Fusion Power Associates Excellence in Nuclear Engineering Award in 1997 and was recognized for outstanding technical contribution to the field of nuclear technology at the International Symposium on Fusion Nuclear Technology in Japan in 2005. Over the course of his illustrious career, Dr. Pietro has accumulated a deep expertise and experience in the scientific, technological, industrial, and organizational dimension of large international fusion collaborations. We are truly privileged to have him share his insight with us today. Dr. Pietro, thank you once again for joining us. Now the floor is all yours, and you may share the screen whenever you are ready.
Okay, so let me now, well, thank you for the very kind words. I'm very honored myself to have been invited to your, to a lecture in your masterclass. And so I think that I have the challenge that not knowing exactly the background that has been explained, I will try to, maybe I will say things that you already are so familiar with, so you will forgive me with that if I will say things that you already know very well. I hope you will forgive me if I do that. But so I will not spend time on things that I am sure that you already know. It would be, I don't know if you can see now the slides or a slide.
That we see the title slide in presentation mode.
Okay, good. So you see what you should see, basically. Yeah. Okay, great. So let me say that it would have been lovely for me to be there, but of course it has not been possible. Sorry about that. But even though I had just 10 days ago, I was in India, but on vacation. So with my family, and it was so lovely to be in India. And I hope I will be able once to give similar lectures in person. So nevertheless, you know very well about fusion. We sometimes say that in ITER we will reproduce what goes on the sun. And I should say that this is not exactly right. I should sort of dispel a bit this. There are important differences between our main reactor. Of course, with fusion, we try to take a shortcut. And we know that the source of all energy, or most of energies that propel our planet and our life, are, say, either are indirect, say, means. Even renewable energies are mostly indirect means from nuclear fusion and our main nuclear reactor in the sky. But in our nuclear reactor, the main fusion reaction is, say, through the proton chain. And the proton chain has a very, very small reactivity rate. The cross-section is so small. And think about that, the fact that the density in the core of the sun is about 150 times the density of water. But the power density is only about 250 watts per cubic meter. And if we would have try to reproduce something we are not able to, but if we would try to reproduce the reaction that goes on the sun, it would be basically useless because the power density is too low to be economically of any interest. So we use deuterium and tritium, and deuterium and tritium has a reactivity which is so many orders of magnitude greater than the one of proton-proton. So we can have power densities which are significantly larger. And I wanted to share with you, the power density question. The power density of, for example, in a light water reactor, fuel element is about 1 gigawatt per cubic meter. That's the order of magnitude. Of course, it's so small. And we can have small power source with the coolant, which is a few millimeters away from the core of the power source. We have, say, megawatt per cubic meter normally burning curve, for example, and we will have about the same order of magnitude in terms of power density in ITER. Now, megawatt per cubic meter is there something we can manage. But what is peculiar in fusion is different from what happens, for example, in a coal power plant, is that we cannot really embed the coolant in a matrix together with the power source. Cannot do that. The temperature conditions are very high. The amount of mass that we deal with is very small. Well, whichever way, one or the other, doesn't matter. We have to absorb the power at the edge. And because fusion or DT fusion is so neutron rich, we end up having a big technological challenge associated with exactly that, with the neutron power flux. And this has made ITER difficult, but it makes fusion difficult in general. Another element is that the radiated power or the conducted power does not distribute itself uniformly. So even in a machine as large as ITER, where we have about, say, around 1,000 cubic meter of plasma in a torus, and we have a surface which is about 1,000 square meter surrounding the plasma itself. So one may say, okay, the power, which is roughly 150 megawatt of alpha heating plus external heating, will distribute itself along such big surface that would lead to, 100 to 100 kilowatt per square meter. Well, that's unfortunately not the case. We are still in a phase in fusion where we have very highly concentrated power fluxes. And I like to say this to begin with, because this at the end is one of the key, drivers, in the design of that has been in the design of ITER itself. So what is ITER? ITER is, it's a prototype thermonuclear fusion reactor. It is designed, it has been designed to reach a thermal equilibrium, and that is a very important requirement. It has driven a lot of the design decisions and even the overall sizing of the machine. And the thermal equilibrium is reached not only in the plasma, okay, where we will have to see that if we reach thermal equilibrium, but that's the idea. But it will have also to reach thermal equilibrium in most of the structures. So because the time constants of the structure range from a few seconds in the high flux components to say about half an hour in the components which are further away, this has basically determined the duration of the pulse, which as a minimum should reach, say, in the order of 10 minutes. 10 minutes will allow to stabilize the plasma itself and to reach, say, stable conditions on the first wall, if not in most of the structures surrounding the plasma. The idea behind ITER is that it should be comfortably designed to reach comfortably, say, ignition or quasi-ignition conditions. So quasi-ignition means that the self-heating should be dominant. So what we call Q as the ratio between fusion power and input power should be about 10. So it means that we will have in ITER about 500 megawatt of fusion power. And out of this 100 megawatt will be the alpha heating, the self-heating of the plasma. And we may have to inject up to 50 megawatts to keep it in these conditions. What we really hope, and what I personally expect, it is like ITER, that it will reach, say, quasi-ignition conditions. So where the alpha external heating power we will be able to reduce it. So there is sufficient margin in the say parameters that we should have, that if things will work as we expect, we will be in that situation. ITER should also try to address the question of, at least in the proof of concept of tritium breeding. We'll do so through the port plugs. It will provide then a lot of know-how, including nuclear licensing experience. So in ITER, we will put about 1 gram of deuterium and tritium, which is more or less the amount of gas that normally would be in the tire of a race bike. And we put it then 1 liter of race bike deuterium and tritium. We put it in 1,000 cubic meter, so 1,000,000 times the volume. See, the aspect ratio of that tire is a little bit different when you put it in ITER, but 1,000,000 times the volume, 1,000,000 times the temperature, and in fact the pressure is about the same. It will be about 10 bar in the core of ITER. Then, of course, to reach that pressure, as you probably have studied in your course, we need very strong magnetic fields. And the magnetic pressure, in fact, that we will have in ITER with its magnet, it's, say, more than 1 order of magnitude, the kinetic pressure in the core of the plasma. And that is really the essence of tokamaks, that this aspect ratio must have a beta, which is a few percent. So we need a lot of magnetic field in order to be able to, yes, confine and stabilize the plasma with even a pressure of about 10 bar. So the project was developed in the 90s and then developed further in the early 2000s. And when it came in the early 2000s, this is also, by the way, when India joined the project. And so glad that you did so. And I hope that you will stay for the long run, as you are contributing tremendously to this project. And this is when the project became more and more a political symbol, not just science research, not only an energy research, but also a symbol of cooperation and let's call it a science diplomacy, which is something for which I would say, notwithstanding the fact that it's introducing some difficulties, it does provide a lot of value to the project itself. I personally am quite proud of the fact that in ITER we have, our 7 flags, and there are not many places in the world where we can show that we scientists and engineers and people can work together with the same objective. This is a wonderful thing that I think ITER represents, and where I want to recognize the tremendous contributions, and I will talk about this a little bit later, from India itself. So that's where, if you would look at ITER, you would see the aerial view of the project. There is on the right side, which is, say, about a kilometer across, there is the switchyard. This is when the power comes in. Unfortunately, it doesn't yet come out, but say this is where the experiment will draw its energy. We have the cryogenic plant. Actually, that is one component where India contributed significantly. We have the magnet power conversion system. And then we have more towards the left, the tokamak building with assembly hall. And then further to the left, the heat rejections and some of the buildings for the heating systems. And on the lower side, where headquarters building is, where the orange arrow points, this is exactly where I am at this very point in time. So in ITER, we have 18 toroidal field coils. The entire toroidal field magnet system will have an energy of about 41 gigajoule. Just for comparison purposes, take into account that the Large Hadron Collider entire magnetic energy is about 10 gigajoule. So it is an impressive amount of energy that the ITER magnet will have. It will operate at a field of about 111.8 Tesla at the conductor. And each coil will have a weight of about 400 tons. And you can see the size. You can see the people under the coils. Those are normal sized people. They are not dwarfs. And if you would see, and you would come, as I hope some of you have done, and as I hope many of you will do in the future, you will see, that indeed, yes, ITER is quite massive. And as some of, I remember, yes, Dr. Saraswat, when he saw this, he said, this is really like an engineering marvel. It is really so. And we have on site now all of the 18 coils. We actually have 19, as we have a spare one. We have on site also all the poloidal field coils, which are there to provide the shape control on the plasma, provide the ability to ramp up the current, and allow to create a divertor configuration. And what you see here, actually, it's the largest of all the coils. This was built on site because it couldn't possibly be transported. Magnetic field here is less. Essentially, coils are made of niobium titanium in this case, while, of course, the one, I should have said, the one of the TF coils are operating at a higher field, and they are niobium 3T. Then we have 9 sectors for the vacuum vessel. The 9 sectors of the vacuum vessel. Okay, we got the 7th one here just today, and we have 2 more to go. They are one in Chieti in Italy, one in Westinghouse, also in the northeast of Italy. They are being finalized, and I was there last week just to encourage the team to deliver the vessel sectors because they are essential for the assembly phase. So we have, as I repeat, 9 sectors of the vessel and 18 coils, meaning that each sector is pre-assembled with a thermal shield and the 2 TF coils before being lowered in the pit. And here you have an image in the assembly hall. On the right side, you see a vacuum vessel sector being waiting to be put on the assembly frame. And the assembly frame is, or the pre-assembly frame, I should say. It is the one that you see on the left side. And there you see another vacuum vessel sector. And if you look carefully, you will also see that there are around the vacuum vessel sector, there assemble the TF coils. The TF coils and the thermal shield between them. We need the thermal shield between superconducting magnets and, say, hot surfaces to limit the radiated power to 4 Kelvin. Otherwise, it would be prohibitive to cool. It would be impossible to cool and keep cold. The magnet would be too expensive. And I hope now you will be able to see an image here, which is the lift of the sector. And here it says the fourth sector moved into the pit this week. In fact, it was not this week. Sorry, I didn't update this slide. This was the third sector being inserted, and I have a movie of that, happened in the 24th of November. And on the 28th of January, we put the fourth sector in the pit, and soon we will put the fifth and then the sixth. So we are moving ahead, and let me see if I... Okay, so we have one more sector to be put in soon, but we had so far 4, one in April, one in June, in November, and January. You see, we are now putting sectors in the pit at the rate of about 4 every year. And it has not been always like that, unfortunately, in ITER. Some of you that have worked in ITER know that there have been times where this was not proceeding as fast as it is now. We have now, as I show you from the aerial view, we have a power conversion system. This converts electrical power coming from the grid to modulated DC current, or say slowly modulated DC current to the magnet system. And there are also power converters which operate at a higher frequency, higher modulation, in order to control, for example, plasma position, to control some of the coils, to, for example, control events such as edge localized modes, or try to control this the behavior of these 𝘚𝑚s and other, say, minor type of magnet system. And say on magnet power conversion, we have essentially all the stage 1 power converters installed and with commissioning essentially being completed. We have a very, very large cryogenic plant that has a refrigeration power of 75 kilowatt at 4.5 Kelvin. Much of this power is to some extent conducted and radiated. Some of it, it's because of the AC losses in the conductor itself. There are many, many sources of heat to the magnet that have to be refrigerated through helium liquefaction. The cryo plant and the cryo distribution is largely completed. Cryo distribution still in the phases of completion, but a lot of work has already been done with a lot of, say, input also from Indian companies. And we achieved liquefaction in December of 24, and we are using now this cryo plant for a test facility. This is the test facility. We decided 3 years ago to build, as a matter of urgency, a magnet test facility, and we have one now. We got the cryostat in October, and as I speak now, we have 1 magnet inside, and we are preparing ourselves for its testing. We will not be able to test all coils, unfortunately, as ideally I would have liked that we could have done, but as a minimum, we will test a few so that we can see if there are some issues that we can, correct. And as a minimum, I think we'll provide a lot of know-how for the forthcoming commissioning phase and anticipate some of the potential issues that will happen then. So myself, I was working in the 90s, and I joined back the project 3 years ago. And maybe some of you could listen to my first talk at the Fusion Energy Conference in London. We had significant issues to deal with at the time, including the fact that we had some thermal shield panels to be repaired, including the fact that we had some vacuum vessel sectors to be repaired. And at that point in time, it was end of 2022, we had 1 sector in the pit It took a lot of time, by the way, to assemble, that we decided to pull out and repair. So it was a very difficult moment for the project because we had underlying issues of quality and quality culture and difficulties also with the regulator who did not quite trust our, say, quality control and quality culture. We had also some assembly contracts that were not going at the speed that we wanted. I mentioned that now we are able to pre-assemble and install 4 sectors per year. At the time, it took almost 2 years to install 1. So it was, say, a little bit too slow, let's put it this way. We had then to repair the components, develop a new baseline, and try to improve the project and design control processes. So I'm glad to report to you today that after 2 years plus of implementation of the new baseline, and also to all the work that had to be initiated in 2023, we have basically restructured massively the organization. And I want to recognize that some of the panelists today have been, say, at the core of this restructuring. And I speak in particular about Arun and Barua that have been contributed tremendously with ideas and with actions in order to restructure the ITER project. But, so many people have contributed. And we have now, say, in March of 2025, an integrated schedule performance index for 24 and 25, of 26. So more than 2 years of 1.03. And bear in mind that this is almost a factor of 2 compared with what we had before. So this is data about plant construction capital growth. And we have implemented in 2025 with an SPI, which is about in excess of 1. We have implemented not only 100% of the planned work, or more than 100%, but we have also implemented 84% more work than ever before 2022. I should say that actually this plot is conservative because the cost performance index that we have now is significantly higher as well. So when it comes here to actual earned value and not payment execution, the difference is more striking. We are trying to prepare accurate information about this data. Now, I decided to give you a bit of perspective in the coming maybe 15, 20 minutes about fusion, because I frequently get questions about, oh my God, look at ITER, is so beautiful, but it's so large, so complicated. And we should be conscious of the fact that this is not per se something that we should do on the long run, but there are reasons for that. So we need, as I said, to reach certain type of performance that requires a certain triple product. And in tokamaks, at the end of the day, the triple product is very closely related to the aspect ratio times the plasma current. And so for our aspect ratio, the plasma current that we shall need is about 15 megampere. Important, again, is this question about the thermal equilibrium, and also to provide sufficient shielding to host a blanket. So there have been, in the history of fusion research, some design proposals, and I pick one here called the PPX that was designed in Princeton in the late 80s, early 90s. This was a burning plasma experiment that was designed to reach thermonuclear condition, but not to have a thermal equilibrium of the structure, not to have the shielding blanket, only to focus on a transient thermonuclear plasma ignition. Maybe not even so transient for the plasma itself, but transient for the structure. I think that these were very smart ideas that were focusing themselves on plasma physics, and they could be considerably smaller because the power flux, when you have to deal with, with transient conditions, can be significantly higher. What you care is more the energy rather than the power, the energy density rather than the power density. So ITER could not possibly operate like that. It had to operate at a magnetic field which is lower, and even if it's quite significant, lower because as you increase the magnetic field, you can indeed reduce the size, you can increase the density, and you can reduce tau, so you can, for a given triple product, balance with a more compact machine. But as you do that, as the fusion power is roughly scaling with a triple product, naturally the power flux is increasing. That has been a very important driver. And another driver is itself the size that it's needed, the space that it's needed potentially, not only to shield the magnet for the neutron flux, but to provide space if one would like at some point to utilize ITER also to demonstrate breeding at scale. This is something which in principle ITER could do at some point in time. Another question which I am asked frequently is, okay, this was designed in the 90s, essentially. The R&D was prepared in the 90s. It was, of course, very advanced and very highly technological R&D done then. But what about if we would do it now? It has taken so long to do it. Would we do it now? Could we do it faster, smaller, and whatnot? Well, here also I have to put some words of caution. There are new technologies now that, no question, could facilitate. And some of them, actually, we are able even to implement in ITER itself. But I don't see any sort of silver bullet that would make a fusion substantially cheaper and more compact. Take into account that in these massive coils that you have seen, in the cross-section, only 4% is niobium-13. Only a small fraction of the section that you see there in the conductor is niobium-13. To a large extent, much of the space for the conductor itself is actually, say, copper stabilizer, copper needed for the to hold on, resist a quench, and of course the helium that it's needed to cool. But the bulk of the cross section of the TF coil, it's needed to resist the magnetic pressure. So it's like a pressure vessel. It's almost 70% of the cross section in ITER is steel for the TF coils to resist mechanical loads. And the steel operates at a very high stress level at 4 Kelvin. It's very, very hard. And I am not aware of any other material that we have developed recently to be able to operate at even harder stress level with such a thick and large forgings. So we are still, in my opinion, in ITER, in the state-of-the-art level. There are I should nevertheless grant that there are important technologies that will be helpful in the future. High temperature superconductor, for example, in my opinion, will provide means to reduce the cost. I'm not so sure about the size, but the cost for sure. They can operate at higher temperature. They can reduce significantly the cost, the operating cost for the magnet, and they can potentially also be cheaper than niobium-13 and the technology associated with that. So a word of say encouragement that ITER remains still, notwithstanding the delays of the project, remains say a modern machine. But the question also that remains is for those of you that want to entertain maybe a life of research in fusion is for me more important about the cost. Well, there is no question for me as an engineer that we have to tackle the question of cost very seriously. ITER has been too expensive. It was more expensive than planned, and it has ended up to be so far too expensive. I have no doubt whatsoever. Part of this cost, one could say, is something to do with the organizational complexity and some political compromises that have been made. Let's say this was a cost that was not for the benefit of the research infrastructure itself, but had other benefits. So it was not just waste money. But we also have to learn about some technical complexity that we have introduced in this project. Part of it is because it is a research infrastructure, and part of it was maybe we did not manage requirements very well. And also, the fact that many things have been done as a first of a kind. But I am putting this slide forward because I think one of the motivating elements for the future of research should be to try to find ways, and this is also research, and maybe some of you may find it boring, but it is still very important, find ways to do things cheaper. And I am convinced that we can do that. And by the way, I believe that the awareness that we have in ITER about what has been very expensive, unnecessarily so, is there. I picked 2 points. First, the magnets has not been, in my opinion, excessively expensive. We could do it cheaper, but it was, say, more or less as planned. But when we go to the more conventional parts, let's say the metallic carpentry, like the vacuum vessel, or the civil nuclear infrastructure, like the building, there, let's say on the building, it has been really over expensive and over delayed. And I should say that maybe counterintuitively to some people, it was not actually because the building is so large. I don't know if you can see in my background the building, and if you cannot, I can show you later. But it's because it's large, but it was tried to compress it too much. And compressing this too much led to a reduction of the volumes, for sure, but the unit cost became very large. So you can reduce, maybe sometimes in engineering, you can reduce the size of something by 10%, and the unit cost goes up by a factor of 3. And this can really happen. And say there are many examples in the history of development of technologies where this compression was excessive, and the unit cost increased. Why? Because at the end, it becomes so difficult to fit components that are to be inserted and supported in the building that the design doesn't stabilize, and the interfaces with the building, which are many, or the supporting structure, keep moving. And the companies that deal with such structures, they are very much welcoming the design changes and changes during the course of implementation. But these things, they are welcoming them because they cost a lot of money. So at the end, the design stability, the design control can drive, from a project management standpoint, the cost unnecessarily high. So I'm telling you this not because maybe this is something that should be necessarily taught in a fusion course, but because I believe that for engineers and scientists that are there to build the future devices, please, let's all take into account the lessons learned in ITER. I should also spend a few words about dispelling the idea that ITER will now, when will operate, will be essentially proving the technology in all its, say, complexities. It's not so. We need to be frank and to be transparent with our stakeholders and with ourselves, and we have to be grounded to understand what are the fundamental challenges. I put the cost as the first bullet. I have spoken enough about that, but I think that we should always put it, say, as a very, very important driver. We have to deal with this question about the peaking factor for the heat flux, and research should be devoted in order to smoothen and spread the heat flux. There is a research in the divertor, there is research in the plasma mantle, but from my standpoint, notwithstanding many years of attention, this has not yet been fully resolved. We have an important line of research on material. We have an important line of research on blanket technology to find ways to breed tritium. As of today, I'm not aware of a design that would be compatible even with the ITER conditions, let alone, say, more compacted designs. And it is a complex area of research where many are strongly engaged, and that will have to be sorted out. And then we have, say, another line which again points to complexity, or better, points in the direction of simplification, which is to make sure that to find ways to increase reliability. I don't want to discourage anyone. On the contrary, I think that we want to make these things work, but it is by being aware of the difficulties that then we can tackle and solve problems. I want to say that in this process of, evolution of the ITER project, we also are trying hard to make ITER more appealing for postgraduates and graduate students. And for those that will finish their master, like you, and then will want to move into directly into the work environment. Our ambition is that, for some time, ITER has been a place where people like me with a lot of experience would come, and we would sort of, die here. It's a sort of the cemetery of the elephants. It's okay when it comes to experience, but a thriving project needs to mix experienced people with those that come and learn and come with new energy. And for me, it's so important that some of you that may come and work in ITER then can move back to maybe to India, to bring back all your knowledge, the knowledge that you have acquired working in ITER, back to your nation and back to the program that I hope India will develop more and more in the field of nuclear fusion. So speaking about India, again, about what has India done for ITER? It's a tremendous amount of work that has been done in India. I can only now have time for a few minutes in that. And here is a view of the main components that India has been responsible of in terms of in-kind contributions. The main one is the cryostat. Now I have only an image of the cryostat because there are so many photos of the cryostat in different parts, but it's it's the largest cryostat ever built, and it was manufactured by L&T in India, transported here, assembled, because some parts could not be transported in its entirety. And you see here some of the packed components waiting to be installed, because the lower part is installed, the middle part of the cylinder is installed, but the upper part of the cylinder and the lid are still there waiting to be installed in the future. We have all the torus cryopump housing, which have been delivered from India. A large, significant part of the in-wall shielding, essentially all of it, which is, relatively complicated, parts of steel that will have to be put inside the vacuum vessel to provide the right mixture of water and steel for the moderation and capture of neutrons in the vessel. In India, the cryo distribution and cryo lines have been built, and cryogenic cold boxes. It is very, very complicated structures with complex engineering and complex conditions. What you see there, cryogenic lines are not at all simple. They have to carry cryogenic helium with minimum heat losses, and to design it in a way which then allows them also to be installed effectively. It's not easy at all. So tremendous contribution in the cryogenic system, tremendous contribution on the cooling water plant, which was also delivered and installed, and commissioning is essentially still ongoing in some parts, but other parts is the system is already working. But also, I should mention, the key industries that ITER participated, participated to ITER: L&T Construction and Heavy Engineering, Inox and Tata Consulting Services and Engineers, L&T Technology and Vacuum Technique, and many, many others that, if you come here, you will see there is a beautiful panel with all the companies in the institute that have contributed to ITER. And if some of you are working there, let me express my deep gratitude. We have also some direct contracts from the ITER organization with supplier. We have a very big contract, for example, with L&T Heavy Engineering, and I'm picking up here a very advanced component that is being designed and built by L&T. That is the result of a decision that I've taken, a couple of years ago, to change the approach with which we will assemble the blanket and develop a robotic arm, say first of a kind robotic arm to assemble the blankets. Tremendous, tremendous, beautiful component that I hope soon we will have here on site for for tests. In India, we had the tremendous work done, and I want to recognize this for the repair of the thermal shield. We had, as I said, 3 years ago, or a little bit more when I came, we found some problems of thermal shield, problem of quality, some stress corrosion presence on the pipe, and Inox India has been instrumental to quickly repair all this thermal shield. The thermal shield were shipped back to India, the cooling pipes were removed, there was some machining around the cooling pipes, they were completely brushed off the silver coating, and then the work was done again. I want to recognize that if it would have not been for Inox, we would not be where we are today, because they did the job very efficiently and very well. There was a work of HMS process vessel. HMS is not Her Majesty ship, it's the hydrogen mitigation system. It is a system to control the production of, say, the handling of a hydrogen that could be produced during a potential in vessel loss of coolant, where the coolant would impinge on the hot components. This is something for nuclear safety driven, that were built, and they are not simple tanks, and they are complicated systems and installed. Another very complicated system is the rupture disk system for the vacuum vessel pressure suppression system. Again, a system that is mostly dedicated to the way we react to in-vessel loss of coolants, and the development of the Ratchet assembly has been successfully tested. And then last, I should say that, a little bit more than 1 year ago, we had here the visit of your Prime Minister together with President Macron. And there is this beautiful picture that I want to also share with you of Prime Minister Modi, President Macron, and we have also here 𝘐𝘯𝘵, and I had the honor to be there, just myself and Macron and non-Indians, and all the Indian team that works in the Indian team, the people from India that are part of the ITER team, that they were of course very moved by the fact that your Prime Minister came and visited and gave us a lot of words of encouragement. And in the background, you see this huge disk. This is not a UFO. This is the lid of the cryostat that we hope to install, say, in a few years from now, when we will have finished the assembly. So I stop my talk here. I have a movie, and I will share these view graphs to you so that you can also use them. But there is an overall movie here that shows the site and well, let's see if I can move maybe a little bit ahead. It will also show the assembly hall, etc., etc. So I will stop talking here, and while the movie plays, I don't know if there are some questions that you plan to ask. I will be glad to respond to anything I am able to. Thank you.
Thank you very much, Dr. Pietro, for that very insightful and inspiring lecture. It is simply fascinating to hear about the progress of ITER and the scale of the engineering challenges involved in such a project of such magnitude. So I'd like to first open the floor to our esteemed panelists. If you want to share your reflections, or if you have any comments or any specific questions to our speaker, Dr. Pietro. So panelists.
Yeah, so I am very much thankful to Dr. Barabaschi. You have given a comprehensive coverage to the progress of ITER project. I'm happy that not only in Tokamak building, but there are many buildings in which a lot of progress has taken place, and many systems have come into the commissioning phase. And one of the important thing what I'm finding that you have started with the nuclear licensing process, and with that process you have achieved such a grand progress that is really fantastic. And you are also taking care of the maintenance aspect that is very important for this program. So on first of a kind system, such a marvelous progress is really commendable. So I really salute you, and I hope that this progress trend will continue and entire world will support you. Thank you very much.
Thank you for the encouragement word, and let me thank, if I may, the tremendous support and endurance also of all, also I should mention the Indian government and the Indian DA and the Department of Atomic Energy. I know that ITER has been in the past, in particular, providing some reflections, let's say, because I cannot really say that this project has always been, very smooth. There have been very rough times, but it was, for me, remarkable. The fact that India has always been very strong, very supportive, and of course, reflections are important also. And through reflections, we also get improved. And this question about licensing for us is of essence, the work leading to licensing, but also the fact that recently, through this improvement in our relationship with ASN, we have been able, and we are in the process of being able now to make some important simplifications. So we are very close to get some important news that unfortunately today I cannot share, but that will allow us to reduce the cost also. We made clear to ASN that in some areas the complexity was too high, and we found now a regulator that is ready to discuss with us and find solutions to reduce, to make things which are fit for purpose. But thank you very much for your encouraging words.
Thank you. Other panelists, Dr. Rajesh.
Yeah, hi. Again, to add to what Dr. Sharan said, thank you for this wonderful talk. It's very comprehensive, and it could be a great boon for all the students who are following your talk. Also, I was very happy to see that, and I want to congratulate you for all the changes you brought in the project, and you've really spirited up the kind of efficiency that you've obtained in this project. I was also very happy to see that you have brought in the private sector in a collaborative mode into ITER, because normally people had this apprehension that the private sector would be a major challenge for you. And because they are promising so many things, they're moving very fast. But I think you've done the right thing of bringing them in a collaborative fashion and sharing ITER's knowledge to them. In the long term, you've mentioned very frankly some of the challenges that ITER is going to face. So there are two things that I would like to comment on. One is this problem of tritium. Now with the new schedule that you have, you won't start your DT operation till 2039 or so. And predictions are that the global stock of tritium will almost reach its lowest point at that point. So have you thought about how to deal with that problem? And the second question, I'll just finish my question, it's a more political one. Apart from the private sector, there are some major national programs that are going to be a challenge, particularly the program in China and their device called the 𝘍𝘶. So if 𝘍𝘶 starts operating according to the schedule, which is next year, and they actually get to 2 or 3 years' time, they start DT operation, what will happen to ITER? Do you have a reaction to that?
Okay, so well, thank you for your words, and thank you for recognizing that the fact that we try to work as to support the private sector. For me, if I may say, it's good that there is competition, and we represent cooperation. but it's also good that amongst that we recognize that, and we means all the team, recognize that we have to work like a startup. We have to work fast. And we have to organize ourselves to be dynamic, to be not to be bureaucratic, to have leaders that move on. And I think we try to do that. And as you could maybe already start to recognize, the results are coming. I think that going back to 2039, my objective is to try to accelerate the project and try to operate with tritium sooner. And I see that there are good reasons why we could do that, not necessarily to reach the thermal equilibrium condition that I mentioned before, but to start to have some tritium operation, because this is also possible. Of course, the amount of tritium that will be there, I am not sure that that other than by accelerating our work, we can do much about that, because that will be largely determined by the source of tritium and some of it by its consumption. Maybe there is a bit of an overestimation about the consumption. And there are hopes on my side that additional heavy water reactors may be actually in the plans, and why not? This will be a way to have the tritium we will need. I don't know if this will be really an issue, in fact. To some extent, I wish it will, because it means that we will need a lot, and it means we will use a lot. It means that the fusion will have reached, say, maturity. Regarding this question of competition and so on, I really wish the best to everyone, including the best. But the best is not a machine which is like ITER. Best is a machine that aims to reach significant fusion power, but it doesn't come anywhere close to the 15 megampere of ITER. Will not have anywhere close to the triple product of ITER. Will have a completely different plasma performance. So best is, in essence, a very nice machine. I very much welcome the fact that it's being built. Nevertheless, even if there would be, all of a sudden a machine that it's built that will have the triple product of ITER, and it's built in half the time and half the size, or maybe by now it will be extremely fast, I will be the first one to rejoice. I don't see for us any other objective than support others. We are using public money, including money from Indian taxpayers, and we have to support Indian companies. We have to support Indian private sector, just as the other private sectors. We try to do that, try our best to do our job and to lead the way in fusion energy. And then, last thing, we have to move fast. We have to get this research infrastructure ready for the researchers as fast as possible. So this should be our focus. Okay.
Thank you. Thank you. Dr. Pietro, how are you looking at the time? How much?
I have another 10 minutes, say 10, 15 minutes. I can stay until, say, 15 minutes from now.
Okay. So one more question from panelists before we move to the questions from the participants. Dr. Rajesh, Arunji.
I did have my hand up. I'll just make it quick. Pietro, thank you for this wonderful talk. Just a couple of quick points. One, I can't resist. The elephant graveyard analogy is very poignant. So I'll have to think about that one for a little while. I wanted to simply comment on your point on BEST, which is that I sat on the BEST as an observer on the BEST advisory committee back in 2023. And they made it very clear that the only reason why they could succeed is because of their participation in ITER. They did exactly what you said, which is they took the experience and the knowledge they gained in participating in ITER and brought it back so they could design the machine quickly. So that's the way that it was supposed to work. And so in that sense, that's a success for ITER. Just to point that out, that was something that they got back. My simple technical question is on erosion of the first well, something I'm very worried about. And all of every calculation I've seen, which points to, for a reactor with solid components, metric tons per year, thousands of kilograms. Do you have any thoughts on this?
So it is in the list, in the sort of list of very big issues. And you are 100% right. The question about erosion, okay, you can see a lot of calculation, of course, and there is also a large degree of uncertainty that we have. So one thing, it's clear that, and that has driven us to drop the idea of having beryllium. Beryllium was, from one standpoint, more amenable as a material, but it would be completely impossible in a reactor condition. And so we thought that the value of ITER, it would have been diminished, and the delivery of valuable information for next steps would come way too late. So that's where we decided to change to tungsten. But you are 100% right. This is a very, very tricky question about what is our first world material. We do not have today a proven first world material. There is absolutely no question whatsoever. And that is proven to resist the erosion condition, proven to, resist to the heat flux, proven to resist to the neutron flux. I mean, it's like very, 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 very complex issues. And this is true for the first world, even more so for the divertor, when we also consider the conditions which in the divertor can be so severe. So it's really, when I started my talk, I said, this is really the problem of power flux. What goes around the power flux? There is really the crux of fusion. And if I may say, this is something which makes me, I cannot say that it doesn't make me sleep at night, because I have other more urgent things that don't make me sleep at night. But let's say this is really a key element. How are we going to solve this in such a way that fusion is an energy source? And if I can spend one more minute on this, sometimes I also think that we should drop a little bit our ideology of seeing fusion as a standalone technology and see, can this technology be simplified on one side and maybe utilizing, say, the fuel cycle and the technology together with what we know about the fission, and fissionable materials and the likes, because this could potentially find itself reduce some of the critical conditions that come on the first world, because we would be able then to operate at a lower power flux, a lower erosion rate, and lower density, and maybe even lower magnetic field. I think the tendency that we have for compaction, it's something which I'm not sure in fusion will work. I think in fusion we have to look at maybe simplification, and the simplification at the conceptual level and at detail levels. But if I go back, this is not to escape your question. Your question is a fair one, and unfortunately, I don't have, a very reassuring and complete answer to this very, very important question, other than by saying we have to work all together on it.
Panelist Arunji.
Yeah, I will have a short one because I think Samik may need time. Thank you, Pietro. I mean, it's wonderful. I have this perspective to be just presented. While ITER brings up what is to be done when we take up reactor as a kind of, course of action, be it governmental, be it private, in the future years. It is also important from ITER to learn what not to do in several areas. And this applies to cost, to technologies, to configuration, several aspects. I understand that to bring out such a dossier or such a kind of document at this stage is difficult. But is there a kind of a map in consideration that we really bring out such kind of say a document which basically kind of guides the right path to the selection? I mean, the cost as well as the other aspects. You have already mentioned and touched upon this in your talk on the costs, but still, thank you.
Yeah, I think that it's quite common, particularly in the private sector, in the public say, domain, that research tends to end with a publication, for example. The academia, this is the standard approach, is to come with a publication. And the publication normally is focused on the success stories. And that is, of course, it's very important and nothing about that. But when we speak about the experience in ITER, the experience in ITER is about, as you pointed out, the success stories, but also the problem or the lessons learned, as it's often put forward. And how we consolidate these lessons learned so that then can be really utilizable and they don't become some sort of like just a book somewhere close to the cemetery of the elephants, but say to have something which is useful, it's a key question. So we had, and I know you have been also to some extent involved, Arun, is on this question about the white book, that concept itself. But I am completely convinced that we need to develop this more. We have to never lose track on the fact that we should consolidate and the data produced, for example, the non-conformities, all the non-conformities during fabrication of ITER, they should be really well documented in a way that can lead the future designers to know what happened and what to avoid. So Arun, I think we have a lot of work ahead of us, and I see this as an ideal job after I will leave this project. You know, when I will grow older, I will have a lot of books to write. But I think apart from these jokes, if I may say, there is also a very good advantage and good advantage, help that we can get from artificial intelligence in this respect, because we have so much data and we have to consolidate the data in a way that can lead the future leaders to acquire this knowledge quickly, to have access to this knowledge quickly. And we are working on that as well, to try to provide the true value of all this know-how that in essence has cost a lot of money. So what has costed so much money needs to be valorized as much as possible, not just the object itself, but all the history that led to it.
And thank you. And also a very robust configuration control that has been brought into the project at this stage also is something which we can, visit in as what is the significance of this system engineering as well as a robust configuration control in terms of such a massive project that you take it. Thanks.
Okay, thank you. So I'll take a couple of questions from our participants. I think the first question you already touched upon while answering to Dr. Rajesh, and it says, can you help us understand the progress that has been made in qualifying tungsten plasma-facing components for erosion resistance, thermal fatigue, and neutron-induced damage under ITER test condition? So I think you already touched upon it, but if you want to elaborate.
Yeah,
something.
I mean, I can spend hours on this, if I may say, and I can spend hours also in particular to highlight the fact that the material at the end will qualify itself in ITER. It is not possible to fully qualify and fully predict what will be the behavior of the tungsten that we will have in ITER. What we can do is that we can see what happens in present-day experiment, which is the conditions of which are very different. The plasma itself will behave in a completely different way. The way impurities will reach the core of the plasma may be completely different in ITER, hopefully much better in ITER than in present-day experiment. So, but this is, let's say, it's a subject that, to be complete, in giving the view of what we know and what we don't know, deserves a talk by itself. So I trust that there are a lot of students there that are specializing themselves in this very important research area, but I don't feel I have the time to provide you with a comprehensive answer. The only thing is that there are some things we know, and there are a lot of things we just don't know, and we will have to find out.
Okay. Question about like program development, let's say as a country, when India is developing its future fusion program in order to contribute to such global efforts like ITER, what should our role be in future fusion programs, whether it is a demo design, superconducting magnets, tritium fuel cycle technologies? As a country, what should we focus on for future fusion programs?
I mean, I get questions here, each one of which would require several hours of discussion in a panel. So I think that the reason why I don't have a very quick answer is because I am conscious that there is a lot of talent in the academia, there is a lot of talent in the post-academia, there is a lot of talent in companies, industry, and that gives a tremendous amount of possibilities in which the fusion program in India could, on one side, be broad enough, and on another side, specialize itself in a specific area. What I think is important from the ITER perspective and how ITER can support, this is a question that maybe I can expand a little bit more. First, I am personally engaged, and I'm very happy to discuss this topic more with you and with those that are in a position to take decisions. That is one area for how it helps, and there are many others here that can do so. Secondly, ITER can provide itself as a platform for people to acquire know-how in an environment which is unique. Because the environment that you see in the assembly hall, there is no other place in the world now that you can get the experience that can be gained here. And you have seen the amount of people and young people. If you look carefully with the lens in that photo, you will see that from India we have a lot of young people, and they will acquire tremendous know-how. And I'm also glad to say that the engagement from India's companies has completely changed in the last 3 years. Just to give you a number, up to 3 years ago, up to the, I must say, to the frustration of Arun, for example, the percentage of contract that Indian companies were getting from the ITER organization were relatively small. So only about, say, between 2 to 3% of the value of the contracts placed by the ITER organization were going to Indian companies. And that was, in my opinion, not acceptable, because in India you have tremendous companies that need to acquire in time also some of the key integration ability. So that should, because the work of doing large research infrastructure is a joint work between laboratories, academia, and industry. And this industry needs to be competent and knowledgeable about the technology itself. And now we are in a range which is more than 10%. So it's more than actually the percentage of cash contributions of India. And I think now it's in a range which is fair. And it's not to provide, say, raw materials. It is to provide components with a tremendous amount of added value. So when I showed you before the robot, that is one area. The area of maintenance and robotics and automated system to maintain the fusion. This is essential for fusion. We not only need to have a tungsten that doesn't erode, but we need also to have maintenance system that allows the replacement of components that are eroded on a fast time scale. You know, this is one way to facilitate the work. And this is one area where I see, for example, the contribution from L&T, once again, going to be important for ITER, but also important to consolidate the technology. So preparing Indian companies. And then I think soon, I hope that there will be a discussions, I hope, in India, something that I personally would very much welcome and to which I would be very glad to participate on the different areas where India can integrate technologies and then get a specific specialty, remote handling or superconductivity or the likes of heating systems. I mean, there are some areas where there is already a lot of know-how. When we speak about heating systems, for example, in cryogenics, this is an area, just to mention two, where in India there is a lot of technology already in hand. But there are others where I believe that more can be done and where in support of the development of a fusion program.
Okay, Dr. Pietro, thank you. There are more questions, but we would like to respect your time and we would like to end this today's session. I thank you all for joining us and for your thoughtful questions and discussions. Our sincere thanks to all the panelists for your added inputs, and most importantly, our deepest gratitude for you, Dr. Pietro, for sharing your vision, your progress, and the challenges of a project of ITER scale. It has been a privilege, absolute privilege, to host you for this masterclass session. Thank you once again, everybody, for being part of today's session. I wish you all a very pleasant evening. Thank you, everybody.
Thank you,
Dr. Pietro.